Atomic energy levels. This shows the lowest 6 energy levels for hydrogen and its ionization energy. When n equals infinity, it's up here, the energy equals 0 and the electron escapes the atom. All the energies are negative. That means the atom is stable and the electrons are bound to the nucleus. There are energies for higher levels of n. Right here you have 6 is also 7, 8, 9, 10, etc. But they're just too close together to draw. As the value of n increases, the energy increases. It becomes less negative. You can see the magnitude is decreasing, but because it's negative numbers, it's actually increasing. Here's a picture of the orbitals over here, right? You have n equal 1, that's the inner one, then n equal 2, and as you get farther away from the nucleus, the n increases. So n equal 1, that's when you're in the ground state right next to the nucleus, right here, and that's negative 13.6 eV. Then you go to n equal 2, all right, that's this green one, and you're at negative 3.40 eV. N equals 3, we follow the blue line up to there, negative 1.51 eV. And hopefully you can see how the energy levels are increasing. They are getting less negative. When an excited electron drops to a lower energy level, right, if you go from n equal 2 to n equal 1, we need to account for the energy that is lost from the atom. This is explained by the conservation of energy. In this case, we have an electron dropping from the n equal 2 orbital here in green, and here's your electron, drops down to n equal 1, getting closer to the nucleus. Let's see what that looks like on the energy diagram. The electron drops from the n equal 2 level down to the n equal 1 level. That's that arrow there. How much energy is released? Well, the change in energy, we always go final minus initial, so the final energy is negative 13.6. The initial is minus 3.40. So we have minus 13.6 minus a minus 3.4 eV, and we get a change in energy of a negative 10.2 electron volts. The energy of the atom has dropped 10.2 eV. That amount of energy needs to be emitted so that the total energy of the system stays constant. It is emitted as light, and that's this symbol right here. What does 10.2 EV of light look like? Well, let's figure it out. We have our wavelength formula here, hc over energy. We put in our value of Planck's constant, and this time we use the EV second version, okay, because why? Because we have our energy in electron volts. Here's the speed of light, here's the energy, and we get a lambda of 1.2 times 10 to the minus 7 meters, or 120 nanometers. This wavelength indicates light in the form of ultraviolet radiation. The same energy that is released when an electron drops to a lower energy level would be required to take it up to that level. So when exposed to white light, okay, here's light coming in. See, this time we have the arrow coming in and hitting the electron. The atoms will absorb bands of light equal to the difference in energy levels. The pattern for absorption and emission spectra are the same. Since electrons can only transition between orbits of set energies, atoms must absorb energy at the same frequencies at which they emit energy. We can use the spectra to identify elements or molecules. And remember, we said absorption and emission spectra have the same pattern, but they look quite different. Here's an absorption spectrum. All right, that shows all the colors of visible light, but the signature of a specific element, in this case hydrogen, shows up as a dark black line. When you look at the emission spectrum, the background is black, but each individual line has the color of that specific wavelength of light. And here's our 400 nanometers going up to 700 nanometers. And this guy right here, that 656 nanometers, that's the transition of an electron from the n equal 3 level to the n equal 2 level.